Wrapping up our day 7 notes. I'm not sure how we ended up with the Bear Grylls problem. What it ended being was he was 18.4 miles away from home, and the angle 53.4 subtracted from 90, he had to go on a north 36.6 degree east heading to undo his southwest trek. All right, again, a problem that you might want to relook at. We'll do a few more of that type starting in a couple minutes. Let's first do a nice simple last component projectile shot with an initial velocity of 205 feet per second at an angle of elevation of 35 degrees. How much of that 205 is horizontal and how much is vertical? Sounds challenging, but if you think about it, it's actually a very easy question. The magnitude is 205 feet per second. The angle is 35 degrees. What do we usually do when you have magnitude and direction? Absolutely 205 cos 35, 205 sine 35. And what do we want? We want the x value to be the horizontal, 167.9, 117.6. But you have to explain that. So the horizontal velocity equals 167.9 feet every second in a horizontal direction. The vertical velocity is 117.6 feet per second, a little more horizontal than vertical. Why? Because the angle was less than 45. Don't stop at the component form. That's how you do it, but you have to complete the question. What's the horizontal and vertical velocity? All right, that wraps up day 7. Let's simultaneously jump into day 8. Let's start off with a nice force vector warm-up. Two forces, magnitude of 36 and 54, act on an object at an angle of 67 degrees. Again, I'm going to make one of my vectors all horizontal, 54, 0. Only use the angle of 67 degrees on the other vector. Let's go black and green today. So the component form of this vector, that angle is 67 degrees. That side is 36. That component form is going to be 36 cos 67, 36 sine 67, which to the nearest tenth, 14.1, comma, 33.1. The sum of those two vectors, r equals u plus v. R as a component form vector, the resultant equals 68.1, 33.1. Again, there was no vertical on the original black. Now we can answer question A. Magnitude of R, square root 68.1 squared plus 33.1 squared equals 75.7. B, the direction, theta, tan inverse y over x. We've done a lot of these now. You should be feeling comfortable. 25.9 degrees. And the reason why I put the big angle at 0, because the question said from the larger force. If I had set them up the other way, I would have had to take that 25.9 and subtract it from the 67. All right, new tool, something very different. Finding the angle between two given vectors. Let's get a visual. Vector u, 3, 4. Vector v, 6, negative 5. I want to find this theta right here. There's a tool in our toolbox we're going to use, okay? It uses what's called the dot product. If I'm given two vectors, u, which is x1, y1, and v, which is x2, y2. The dot product, u dot v, equals x1 times x2 plus y1 times y2. So we're going to end up with a single numeric value. So in this case, if I wanted to find the dot product of those two vectors, 3 times 6 plus 4 times negative 5, 18 minus 20 equals negative 2. That would be the dot product. But that still doesn't find us the angle between the two vectors. But we can use it. The angle between two vectors, theta, is equal to cosine inverse of the dot product of the two vectors divided by the product of their magnitudes. Quite a complex formula, but we can do it. All right, that same example we had a minute ago. Again, to get a little bit of visual, 3, 4, 6, negative 5. We're looking for theta. We now know that theta equals cosine inverse of the dot product of u times v over the product of the magnitudes. We just found the dot product to be negative 2. The magnitude of vector u, 3, 4, 3 squared, 9, 4 squared, 16, 9 plus 16 is 25, square rooted, that vector right there is 5. Vector v, 36 plus 25, that vector is radical 61. I'm going to leave it like that because it's going to go right in here. And now I'm going to take the cosine inverse of that. Cosine inverse of negative 2 over 5 radical 61. In my calculator, the angle theta equals, to the nearest degree, 130 degrees. Let's take one more example of this new dot product. I don't know if we need to do two. Sketch it up. Vector u, 2, 5. Vector v, negative 6, negative 2. I'm going to look for this vector angle right there. I'm going to guess it to be obtuse for sure, maybe somewhere close to 170, 180 degrees. Let's do it. Theta equals cosine inverse of the dot product. Let's do our dot product right here. 2 times negative 6 plus 5 times negative 2. Negative 12 plus negative 10 equals negative 22. That goes on the top. Magnitude of vector u, 2 squared is 4, 5 squared is 25, radical 29. 6 squared is 36, 2 squared is 4, radical 40. I'm going to leave it just like that and put it in my calculator. Theta equals 130 degrees. Oh, wait a second. Hold on. Let's back it up. A minute ago, I read the wrong angle. That blue one up here, I'm sure you were wondering why you got a different number. Cosine inverse of negative 2 over 5 radical 61 is 93 degrees. I was going to say, I didn't think they would both be 130. All right, since I messed up, we better do one more. I'm not going to draw it this time. Theta equals cosine inverse. Let's do some good mental math. Dot product. Negative 6 times negative 2 is 12 plus 3 times negative 7 is negative 21 divided by 36 plus 9 is radical 45 times 49 plus 4 is radical 53. You could do a little bit of simplifying in there if you wanted. Turn the 12 minus 21 into -9, or just throw it in like that. The angle theta to the nearest degree is 101 degrees. Very valuable tool. Will require a little memorization, but I think it's something we can do. All right, one more application, what we started on yesterday. Putting all of our knowledge of vectors, ships, airplanes together. Let's see if we can do it. We've only got about 4.5 minutes. We might not finish it, but we can always finish it tomorrow. Ship, call it vector blue, traveling at 40 knots, a nautical mile per hour at a north 10 east. So north 10 east is going to be first quadrant. I'm going to make that magnitude 40. And I always convert the north 10 east to math talk. North 10 east is 10 to the east of due north, otherwise known as 10 less than 90, which is 80. So to find that vector, I'm going to go 40 cosine of 80, 40 sine of 80, which I have to equal 6.9, comma, 39.4. Now let's do the current vector in red. Northwesterly, no number. That means 45. 5 knots, there's my velocity. I'm going to try to draw it to scale. 5 is a lot shorter than 40. In the second quadrant, 45, northwesterly would equal 90 plus 45, otherwise known as 135. So vector red is going to be 5 cosine 135, 5 sine 135. Let's get rid of that 5 there. There we go. All right, that vector becomes -3.5, comma 3.5. Again, we expected it being 45. We now got to find a resultant. Use that good old parallelogram method. Copy red, copy blue, resultant in green. R equals U plus V which is 6.9 plus -3.5, 3.4. 39.4 plus 3.5, 42.9. So we've got resultant in component form. We now got to find the ground speed. That's A. Magnitude of R, square root 3.4 squared plus 42.9 squared equals 43 nautical miles per hour, knots. We'll get direction by tan inverse of 42.9 over 3.4, which is 85.5. But don't forget, we got to subtract that from 90. 90 minus that equals north 4.5 degrees east. Always off the vertical. All right. There's the 2 new questions. What is the vector to compensate for the current? What is the heading? What heading does the captain need to take to compensate for that current to remain on course? This session's almost over, but I will say this. Vector C, or question C, instead of taking the current vector, which we had as -3.5, we are just going to negate it to compensate for it. So the compensation vector would be +3.5, comma -3.5 to offset for that current. We would then just simply add that -c to the original ship vector, and that would give us our compensation vector where we would aim. Good place to call it for today. We'll pick up one more day, day 9, on some final applications and our vector knowledge. Thanks, guys.